Welcome back. So now we'll have 3 shorter technical presentations, also on software-defined networking. And first, I'd like to give the floor to Stefan Hagdahl, who got his PhD at KTH, and he has been working at SAAB as a program manager for many years, trying to use software-defined networking to make the next generation secure networks.
Thank you. Yes, so 15 to 20 minutes, three slots here for an hour. As Cyril said, who I've known for many years now, I'm going to talk about software-defined networking from an industry perspective, of course. And I will talk about things that I, in principle, don't know so much about, the wonderful technology of 5G or 3GPP technology that we have been using for many years now. And after me, Ericsson will come and tell about these things much. They know about these things much better. But for me, it's very important because I think there is opportunities to use this technology in defense domain. So 3 or 4 slots here in my presentation introduction and some kind of analysis, not the level of Nate explained to us here, but some kind of analysis. Some short slides on programmable networks that we will discuss more about. And finally, I will highlight what we are going to do, Ericsson, SAAB, and some other companies within the 5G area. And we call this 5G Compad. So, as you probably know, SAAB is in the defense industry, and we want to produce products that are useful when there is no conflict and when there is a lot of conflict. And this, of course, changes in space, in different places, or in time. But if we produce products that survive under the worst conditions, our customers will be very happy. And the threats against our products and systems comes from many different directions. So 5G, I found this picture. I thought it was quite illustrative when it comes to 5G or 3GPP technology for defense. Maybe you know about this Howard Carter, and he came a century ago into this cave under the pyramid and found all these treasures that has been there for a very long time. And for the defense industry, it's the same thing. The 3GPP technology has been there for a long time. We have discussed it, how it can be exploited, and I think now it's the time to exploit all these treasuries. But our customers use our systems in an environment where there are a lot of opponents with lots of resources that want to destroy these things. And that, for that reason, I want to emphasize that we work with defensibility, the requirement on safety, security, and survivability. That is extremely important. So there is a reference down here that I've taken this graph from. So now to the analysis. What is the rewards for our customers if we manage to bring in 5G for defense? Interoperability. As you know, in the civil world, 3GPP technology enables us to talk to anyone in the world. There are similar initiatives within the defense domain. Economy of scale. Even though lots of countries spend a lot of money in defense products, that is not the same level as we have in the civil world, so to say. So if we manage to exploit these technologies, bring it into defense, we will, in the end, as we say in defense domain, be able to turn this wheel around here, observe, orient, decide, act, faster than our customer's opponent. That is what it's all about. So if we can bring in this interoperability capability, if we can exploit the technology recurrently, then we will probably be able to create new capabilities in the defense domain or defense utility. So 3 happy smileys up there to the right. What is the problem? The problem is that 5G, 4G are built for billions of people, hundreds of countries, hundreds of operators, lots of complex use cases. And I illustrate this by this pile that symbolizes the software stack, which Nate told us, lots of lines of codes. And we are asked to bring in that technology into the jungle, where there are animals, if you see what I mean, that are capable of doing things with a lot of resources. So this is a complex machine, bring it into a very hostile environment. So now I have 3 slides on complexity. The first slide on complexity. As you know, you will know better than me, being in software domain, if you have a software program, it can be changed to any other software program if you get access to the source code, so to say. So if you buy a product, someone gets access to it, it can be changed. It doesn't cost so much to add 1 more million lines of codes into a system. So from a developer or supplier chain, to take down open source, make it 1 million lines of code bigger, the cost of that compared to adding a new hardware thing is much less. So there are no hurdles, or there are no big hurdles adding more complexity. And finally, as you all know about virtualization, having workloads, sharing hardware will cause problems. Can cause problems if you get your opponent into your computer. So what our customers and our industry are used to when we think of our customers' opponents is, well, we think of that cannon, and we try to fight back with fire, we try to move around, or we try to add panzer or other things. This is what we are used to. But adding a lot of software to our systems and thinking of that component instead, we should think of having a building redundancy, like I explain here. We should think of our system as a house of cards instead. So, and that is a totally, from an engineering perspective, it's a totally different problem compared to this. And that is why I say that the threat landscape increases a lot in diversity if we add these big machines or big complex machines. Another picture of complexity here. All you know about the software supply chain. We know about the hardware supply chain that we had for many, many years, where we need to make sure that every level in this supply chain should be okay to make the system work in the end system or in the end environment. But now we add a lot of software, and then I added these words instead, corresponding to these hardware-oriented words. And we want to make sure that we have availability all the time. And as we know, the deeper this supply chain gets, the more complicated it gets. And for example, for the opponent to destroy things, it gets quite not easy, but there's a lot of way of destroying things. So that is a sad man up to the right there. As I said, we want to have economy of scale, but there is a backside of that, of course, because the economy of scale tells us that new functionality needs to be added very fast to win markets, so to say. So the systems are changing very quickly. And the reason for that are many. One is that you want, or one driver for the hyperscalers is to move, of course, workloads up in this hierarchy, and maybe finally to the upper centralized cloud here. So a lot of money is spent in moving workloads upwards here to decrease the cost of floating point operations and memory store and compute. But the problem for our customers is that if you have two workloads, one that you trust a lot on and one workload that you don't trust so lot on, and if you move those workloads upwards in this hierarchy, they will get closer and closer to each other logically, physically, and you need to work a lot on isolation between this yellow and red workload. So if we want to exploit this way of moving workload upwards, then we need to invest a lot in isolation techniques. And there is another aspect of this also. As you move the workloads upwards, you can think of every dotted square here as you put things in the same place, and then you get, as we call, a single point of failure, a kind of single point of failure. Each time you move it upwards, it will get easier for your opponent to destroy that and destroy a lot more things than he or she could before. There's another picture of that here. So we have a centralized asset and a two distributed assets, and we want to decide where to put our workloads. We used to do it in the far right, and now we should move it upwards. And as we do that, we get a single point of failure. And, well, the network gets more complicated as we add centralized compute resources. The way the information flows in the system gets much more complicated. So what I've tried to explain here, is that there are two sides of the coin, it says. You have the rewards, you have the interoperability, you have the economy of scale, you can overtake your opponent's observe, orient, decide, act loop. But you get complexity, you get a difference in velocity. You don't want to have all this technology coming to you. And finally, you have you will get a single point of failure. So we need technology that will make these problems less hard to attack. And this is my ideas, what you should focus on. This big complexity that we add to the system needs to be loosely coupled, so you don't infect the original system, so to say. And that you sustain resilience in your system. So if that one breaks, it should not infect that one, so you can use that still, even though you have infections. You should lock down functionality at build time to minimize configurability during deployment. We need to acknowledge that our customers, they don't want to spend time in front of a network. They want to do other things. And of course, work really hard with the software supply chain. And we think that one of the pills to do these things is software-defined networking or programmable networks, as I say here. Nate already mentioned these things, but we know there are a lot of compute resources here, and now we have a programmable chip for networks, which is, I think, a good starting point. Then we can get a higher pace when we try to, it is our customers that run the ODA loop, but we also do that in some sense. We learn what the opponent can do, and we want to adopt. So instead of waiting years for standardization organizations, we want to do this quicker, so we can adapt. I skipped that one and summarize the pain reliever, so to say. Mitigate complexity, work hard with the isolation safeguards, work with the software supply chain, make sure that you have really well-defined backup network clones, be able to timely patch, and you need to have transparency. As Nate also explained, you can look at the code, you can formally verify it, and observability during runtime, of course. Finally, 2 slides here, 5G. This technology and these hurdles that I explained, we want to work with that with our European industry ecosystem, Ericsson, Nokia, and others. The list of companies here involved. And we call it 5G for communication and peacekeeping and defense. It's a 3-year project and will hopefully start the 1st of December. And what we have told the customer value that we have told our customers is 3 things. It will give our customers reinforced interoperability. It will sustain information superiority on the battlefield. And we will base it on technology in Europe where 2 big telco companies have their main offices, Nokia and Ericsson, which is good from a European perspective. Thank you.
Thank you, Stefan.